Differentiability and continuity. Recall that the derivative means the slope of the tangent line. A function is differentiable at a point if you can take its derivative at that point. In other words, you can find the slope of the tangent line. Now, there are three conditions that destroy differentiability, which means make the function not differentiable. You've got a sharp turn, a vertical tangent, and a discontinuity. Let's talk about what a sharp turn looks like. This is a picture of a sharp turn. Notice that there is a slope on the left side of the sharp turn, and there is a slope of the line on the right side of the sharp turn. However, this slope is negative and this slope is positive, so clearly these slopes are different, and when we get to this point, we cannot draw a tangent line, and therefore we cannot find a slope at that point. So we say the limit as x approaches that x value of the derivative does not exist, meaning the slope as we get closer to that point does not exist because the slope coming from the left doesn't equal the slope coming from the right. Again, the limit of the derivative doesn't equal the limit of the derivative coming from the other side. So again, this is saying the slope of the function, the slope of f from the left is not the same as the slope, remember derivative means slope, of f, the function, from the right. Notice this slope is negative, this slope is positive. Negative slope, positive slope. Even if they are both positive, they have to be the same slope values. The vertical tangent destroys differentiability because the limit of the derivative does not exist like this, but for a different reason. This time, the limit of the derivative as x approaches some value is positive or negative infinity. Notice in this picture that the slope of this line as we're looking is positive and it's getting steeper and steeper and steeper, and now the line, if we were to draw a tangent line, would be vertical. Therefore, the slopes are increasing without bound as we come from the left. Similarly, the slopes are increasing without bound as we come from the right. But these slopes, right at that point, the slopes do not exist. And even though we can draw a tangent line, we can't find a slope of that tangent line. This time the slope, I'm going to call it m, is undefined because it's a vertical tangent line. Let's look at the last condition that destroys differentiability, if a function is discontinuous. Remember our three parts of continuity, the function value has to be defined. Well, in this example, the function value is not defined. We can't draw a tangent line at a point that doesn't exist. Second, that the limit has to exist. If it doesn't exist, then the function's discontinuous. That would be like here, the limit doesn't exist. I can't draw a tangent line at this x value. And finally, that the function value equals the limit. So if it doesn't equal it, like here, the function value is down here while the limit is up here, I cannot draw a tangent line. We have to have a smooth curve to draw a tangent line, and that tangent line has to have a slope, unlike this graph in the second condition. Let's take a look at some examples. So from an AP exam, we'll read the following. The graph shown below has a vertical tangent at 2, 0. So here is our y-axis, let's label. Here is our x-axis, let's label. And at 2, 0, they're telling us this is a vertical tangent. So we don't have to guess what it looks like. We know that the slope there will be undefined. And it has horizontal tangents at 1, -1, 1, -1, horizontal tangent. That's okay. Slopes are 0 at horizontal lines. And 3, 1. 3, 1, again, that's okay. The slope is 0. For what values of x, for -2 less than x is less than 4, is f not differentiable? So we look for some of the conditions. As I scan from left to right, I notice one of the conditions right here, the function is discontinuous. So at x equals 0, there is a discontinuity. So that's one of the places where the function is not continuous. Where else? Where we have a vertical tangent. That's at x equals 2. Remember, they asked for the values of x, where the function is not differentiable. So there is a vertical tangent at x equals 2. And let's practice writing what that means in terms of limits. The limit as x approaches 2 of the derivative of the function equals infinity. The derivative, the slopes are increasing without bound. We've done our answer, but we can answer this another way if asked. The function is differentiable on the following intervals: -2 to 0, union 0 to 2, and union 2 to 4. Remember, we're only going from -2 to 4, and these are the two places where we have a not differentiable location. Let's take a look at the second one, also from an AP exam. Let f be a function such that the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h equals 5. Which of the following must be true? Must is an important word. Not can be true or might be true, but has to be true. So remember our limit definition of the derivative. That's what this looks like, and it's really important to recognize that. So that part means that the derivative of f prime, at the x value 2, then the rest of it right here equals 5. So f prime at 2 equals 5. What does that mean? That means the derivative, I'm going to abbreviate, the derivative of f at x equals 2 is 5. What does derivative mean? Slope of the tangent line. So the slope of f at x equals 2 is 5. Just another way to say that. So let's take a look at our choices. When it's written like this, we can choose more than one of these answers. Is f continuous at x equals 2? Well, I'm not quite sure until I examine this second one. Is f differentiable at x equals 2? Well, we just said there is a derivative at x equals 2. So yes, f is differentiable at x equals 2. Therefore, the function has to be continuous. Because remember, when the function is not continuous, it can't be differentiable. In fact, let's go back to our notes above and make that really important note about continuity. So when the function has a discontinuity, it won't be differentiable. If not continuous, again, I'm going to abbreviate, then not differentiable. So the contrapositive is also true. Therefore, if differentiable, so if the function's differentiable, then the function has to be continuous. It has to be. So differentiability implies continuity, and that's a really important idea to take away from this. Let's go back to our problem and look at the third part. The derivative of the function is continuous at x equals 2. Well, we know the function is continuous, but we don't have enough information to tell that the derivative of the function is continuous. So it's just choices 1 and 2 only. We're going to select C for that reason. Number 3, answer both parts below for f of x equals this piecewise function given here. Part A, show that f of x is or is not continuous at x equals 0. So remember, our definition of continuity starts with, is the function defined at that x value? Well, f of 0 we get from this part of the function because x equals 0, x is greater than or equal to 0, so we use this part. So plugging in 0 into that expression, negative 0 squared plus 4 equals 4. So there is a function value at x equals 0. How about a limit? The limit as x approaches 0 of f of x. Does that exist? Well, in a piecewise function, we have to look at from the left and we have to look at from the right if we have a less than and greater than situation. So first we'll do the limit as x approaches 0 from the left of f of x, and that's going to be this expression with 0 plugged in. That equals 1. And then we'll do the limit as x approaches 0 from the right of f of x, and that's going to use the bottom expression, which we also had to use for our function value, and that equals 4. Notice these two are not equal, which means the limit as x approaches 0 of f of x does not exist. Therefore, the function is not continuous. F of x is not continuous at x equals 0. It fails that second part of the definition of continuity. Part B, prove that f of x is or is not differentiable at x equals 0. So remember how differentiability is dependent upon continuity. Since our function is since our function is not continuous, we know that it cannot be differentiable. At that point, x equals 0. And there you have it.